We've got a good number of attendees here. Just wanted to welcome everybody to this webinar. So today we'll be focusing on AC interference, specifically with pipelines. It's part of EasyPower's series on different power system studies, and very much appreciate everybody's time today to learn about this topic, and feel free to ask questions as we go through. We do want to start this webinar with a series of polls, so if you don't mind, please do let us know a little bit about your experience. So we'll launch this. So the first question is, how familiar are you with AC interference? So I'll give a minute for people to put in their responses. And certainly appreciate everybody putting in a response, because it helps us direct this webinar so we can help people a little more specifically for where their needs are. And we got most people voting in, so I'll go ahead and close this. So you can see here the majority of people are familiar with the terms and the concepts. Some are new to the subject, and we have a 0 on evaluating AC interference on a regular basis. So we'll go ahead and go into the next poll question. And we have 3 poll questions today. So the next one is launching. So here we want to understand, have you attended other AC interference training in the past? Looking to understand if you've had some internal training at your company, you've had some external training that you may have attended, or if this is the webinar that you're looking to learn some more information from. Again, I'll give it another few seconds before we close the polls, and I'll share the responses. I'll go ahead and close that. So as you can see, a pretty good crowd here. Everybody's generally looking to learn from this webinar, which is great, because we're going to go through first the basics of AC interference, or the general concepts, before we go into some practical application of using XGSA Lab in analyzing these systems. And this is our last poll question. This may not be as applicable given the audience, but it is asking which challenges affect your studies the most. So I think this first bullet point is going to be the most popular given the voting so far. But common themes that I hear in doing these discussions is developing models, analysis accuracy is a challenge, and really developing effective mitigation methodologies. Again, appreciate everybody that can take a moment to vote. It helps us understand where the audience is at. I'll give it another couple seconds before I close and share the poll. Okay. I think most people voted on this, and so we actually have a decent spread. Obviously, majority of people are new to the subject, so we don't really have a baseline for the challenges of the most challenging aspect of the study, but a good sprinkling into the other categories as well. So with that, again, want to thank everybody for jumping on this webinar this morning. Today, we will be discussing AC interference with relation to pipelines and stepping through the XGSA FD analysis software so that we can give people an understanding of how to perform these studies. My name is David Lewis. I'm an engineer here at EasyPower, and I do want to invite everybody to put in questions as they come to them into the question bar. At the end of this webinar, I will look at those questions and be sure to respond to everyone. And if I don't get to your question during the webinar, I will make sure to follow up with you on the email. So please do, if you have any questions, curiosities, enter them in there. We also have a survey at the end of the webinar that I definitely appreciate if you can stay on and let us know what you thought of the webinar. So with that, we'll go into the presentation half of this. So this webinar, we're going to have it split up. First half is going to be a little bit into a PowerPoint, stepping through the basics. The next half will go into the software. So the main purpose of this webinar today is really to discuss the primary concerns related to AC interference in shared corridors with pipelines. And my goal is to provide some techniques for analyzing these studies with XGSA FD. So at the end of this webinar, it's my hope that you'll be able to describe the physics of AC interference and share that information, explain the pipeline hazards related to AC interference, and determine mitigation approaches for resolving any hazards that may develop from these shared corridors. And really, we're going to use the kind of integrated workflow of XGSA FD to analyze these types of systems. So to complete those goals, we're going to follow this outline. We'll first talk about AC interference, just the general physics of that, and go into describing how we can couple to pipelines and what hazards can result from that. After we've covered those kind of bases, we'll be able to go into actually how a study is performed with XGSA FD as far as how we can build a model, and then going into the evaluation of those calculation results. So first I want to talk about physics of AC interference, and we're going to go into 3 different types of coupling mechanisms. So the first type of coupling mechanism is described as the inductive coupling mechanism. This is driven by the magnetic field, and this is what primarily is the cause of AC interference for many shared corridors with pipelines and transmission lines. So we have an alternating current that produces a magnetic field, and that magnetic field will induce an opposing voltage and current on parallel metallic objects. So when you have a transmission line running for several miles and a pipeline running parallel to that for several miles, you can have that induced voltage effect. Another coupling mechanism is the capacitive coupling mechanism. This is driven through the electric field. So it's going to be your voltage of your lines that's driving this coupling mechanism. This effect really isn't as significant for most pipelines, given that most pipelines are buried below the Earth's surface, so that reduces the electric field strength at the pipeline's buried depth. Of course, if you do have a pipeline that is above grade, then this capacitive coupling can be a significant effect and can be a concern when you're in the installation period of a pipeline, as that may be above grade before it's actually buried. And the final third coupling mechanism that we'll talk about is the conductive coupling. So this is most often associated with fault conditions, where we may have a fault on one of our towers or at a substation, and that produces current flow from our tower grounding system, and that can conduct to our pipeline. As illustrated on the right, we have maybe this tower or one of the towers ahead or behind has a fault on it, and then that current may go through the earth and conduct to the pipeline and creates a ground potential rise and possible hazardous voltages. So really, we're concerned about these 3 primary conductive, or these 3 coupling mechanisms from a transmission line to a pipeline. And when we think of a transmission line, the majority of the time, it's in a steady state operation, which means that you have 3 phases that are operating in a vectorially separated manner. So we have, let's say, phase A, that is 1,000 amps at 0 degrees, phase B, that may be 1,000 amps at 240 degrees, and phase C, that's 1,000 amps at 120 degrees. So this phase separation leads to some balancing in the overall magnetic fields. So as you get the phase conductors closer together, you have greater cancellation in each of the magnetic fields, or the magnetic field along the right-of-way. Well, the opposite is true. Is if you have greater phase separation, you can have more magnetic field as a result of that, and therefore higher induced voltages. And we can kind of see that in this chart. So on the right, we have the magnetic field if you were going across the right-of-way of a 345 kV line or a 115 kV line. And the main difference between these two is just the phase separation. So the 345 has more like a 30-foot separation between each phase, while our 115 is separated by 20 feet. Because this greater phase separation, our nearest phase conductor is going to have a more significant effect on the magnetic field across that right-of-way. And generally what we see is higher voltages will require greater spacing between phase conductors, which means greater induced voltages on parallel objects. Another thing to be aware of is that your phase arrangement is going to augment your magnetic field along the corridor. So we have previously looked at the delta configuration, which is illustrated here in the orange line. So we can see the magnetic field of that. If we have a simple vertical tower configuration, meaning each phase is stacked on another, we have a little bit different magnetic field profile across that corridor. Now, if we have a horizontal phase configuration, we end up with relatively larger peaks of magnetic field that is driven by the outermost phase conductors, while the central point, that's where we see the greatest cancellation, and so we see a significant reduction in the magnetic field right in the center of our corridor. And then if we have a double circuit transmission line, if we phase this properly, meaning if it's phased A, B, C, and then C, B, A, we can cancel much of that magnetic field and end up with a profile more like this blue line. The double circuit, though, you do need to be aware of transmission lines may take an outage for maintenance purposes or unscheduled outages due to a fault. And in those situations, you may end up with a double circuit line that actually should be evaluated with the conditions of a vertical configuration, because when one of these circuits is out of service, this is the configuration you end up with, and you lose that magnetic field, we'll call it balancing. And then we also have the faulted conditions, and in faulted conditions, we kind of talked about this in the conductive coupling mechanism. We have a lot more current going down one of our phase conductors during a short duration of time. What that means is a greater magnetic field, and that results in a short duration of much higher induced voltages and possibly conductive voltages. So I want to talk a little bit about other recipients before we dive into pipelines and go into actually modeling approaches. So typical recipients for AC interference is other transmission and distribution lines. Those are parallel metallic objects, and it can be a hazard if we have maintenance on one line where we can induce or capacitively couple voltages from our energized lines to our de-energized lines. Obviously, in this webinar, we will focus on pipelines, as those are metallic objects that often run parallel to these transmission lines for several thousands of feet. Railroads, cables, vehicles, and even some buildings can also be recipients of AC interference hazards. So the analyses can vary pretty dramatically based on what type of recipient you're looking at. But from a pipeline perspective, there's a few things that we typically look at. So information that you want to understand about a pipeline is its appurtenances. And these are all of the parts of the pipeline that may have some sort of personnel interaction. So that's going to be your pump stations, your test sites, your valves, all these locations where you might have individuals making more contact with the pipe rather than the buried pipe itself. Also need to be aware of the material of the pipeline. Obviously, it doesn't need to be evaluated if it's a non-conductive material. If it's a steel and what thickness that steel may be and what diameter that pipe may be will affect the overall induced voltages and how much voltage can be induced and conductively coupled. Additionally, most buried pipelines will have some sort of coating on them, and this coating is to protect that metallic pipe from corroding in the soil. And the challenge, or part of the problem, is that that coating also allows for greater induced voltages on the pipeline. So understanding those characteristics is also going to be important for evaluating AC interference from transmission lines to a pipeline. The typical issues that we're concerned about for steady state scenarios, meaning the power system's operating normally, would first off be personnel safety hazards. Typically in North America, we look at touch voltages with a range of 15 to 50 volts. Typically this is associated with the appurtenances, but it will depend on the individual entity and what their preferences may be for that safety criteria. There's also concerns about the pipeline integrity, and there's a corrosion known as AC corrosion, and this is the phenomena where you have an induced AC current on your pipeline, and that can lead to accelerated corrosion on that pipeline. Wherever that coating may have a small nick during installation, you can have significant AC voltage there that leads to much faster degradation of that pipe. So a pipe that may be installed to last 50 years can corrode in 5 years. So it can be a pretty significant issue. And typically the minimum value that we look at is 30 amps per meter squared. This does vary by entity as well as whatever their cathodic protection process may be. So, but 30 amps per meter squared is typically the minimum value that would be reviewed or a concern for AC corrosion. During fault conditions, this is a much shorter duration of period that we need to be concerned about, but one of the primary concerns is personnel safety. And we'll look at, again, a touch voltage hazard. However, this touch voltage is for a short duration with a much greater magnitude. And typically the criteria for this is taken from the IEEE standard 80. This standard is associated with grounding of substations, but it provides criteria or calculations for determining how much the human body can withstand of this shock voltage. So we can have 1,000 volts on a piece of equipment, and somebody's feet may be at a potential of 800 volts. So that would be a 200 volt touch voltage. Again, we have concerns about the pipeline integrity. With the much greater voltages in the soil, you can have coating stress issues, meaning that you can have several thousands of volts in the soil, and the pipeline may be only a couple hundred volts, and that may be sufficient to exceed the dielectric strength of that coating and puncture that, leading to future AC corrosion concerns or just general corrosion concerns. And if there's already some nicks or damages in that coating, you can have direct arcing from the transmission system to that pipeline. And that cannot, both of these can obviously be pretty hazardous scenarios. So we'll get into the next stage of this webinar where we're actually going into the software and developing a model. So what we need to do is get our data first. And this is going to include the plan and profile of our transmission line, those phasing arrangements, whatever that conductor information may be, as well as the load and fault current for that. On the pipeline side, typically needing the pipeline arrangement, any appurtenances associated with that, as well as the coating characteristics of that pipe. And the analysis process is really you kind of develop your base models to start evaluating your steady state scenarios and your faulted state scenarios. Once you've evaluated all of the results, if there's need for mitigation, that needs to be incorporated and then reevaluated through each of these different scenarios or states before reporting on that. So I'm going to close this, and I do want to first show the type of information that you might receive if you are perform an AC interference study. So the first thing to be familiar with on the pipeline side of data is a pipeline arrangement plan. So this is our alignment drawing. This is going to typically have a satellite view of the pipeline's path. It can incorporate other little details, such as the appurtenance locations. And one thing that's useful is if you look down at the legends, they will often note other entities that are known in their corridor. So here we can see in the legend, this power line is a part of their alignment drawing, and we can scroll up to see that little P with the dashed line associated with it. This shows us our general alignment for our pipeline and our power line. Typically, you'll also have the stationing drawn here. So this 50 plus 00, 40 plus 00, this would be interpreted as 5,000 feet, 4,000 feet, 3,000 feet. And you also get information about the pipeline's dimensions as well as the coating material that's being used. So this is a pretty good source of information for all things related to the pipeline. On the transmission line side, we'll usually request a plan and profile or get some sort of export from a DXF file. But it's a similar type of information that you receive on the pipeline or to the pipeline. This is called the plan profile. So you'll often have a image of where the towers are located. And this gives a little satellite imagery as well. So you can kind of get a top-down view of the transmission line's path. Then we have the arrangement of the phases. So here, this shows the elevation or the height of the tower itself, the phase conductors and their separation, their attachment points, as well as the sag characteristics that's illustrated here. So we can tell that this phase conductor has this attachment and may sag 20, 40 feet, typically illustrating the maximum sag characteristics, either due to maximum loading conditions or maximum loading conditions with some sort of physical ice loading or wind loading. So that gives us an understanding of the minimum earth to phase conductor separation, which can yield a more conservative AC interference analysis. So that's kind of the general information that you would get. And one way to incorporate or design your model, you can open up a CAD program and start placing those plan profiles into, or the alignment drawings and plan profiles into this, so that you can simply follow the path in a tool like MicroStation and follow along with the pipeline. And you can stitch these drawings together if this is the type of information you may receive. And every case tends to differ by the entity as far as what information they're willing to share and what format they can share that. Obviously, if you get it in a DXF format, that's fantastic because that's something that can be immediately imported into XGS Lab. One cool thing or a great feature about MicroStation that I use semi-often is that you can actually use the Google Earth or more satellite imagery to help draft your system. So you can set a coordinate system in MicroStation, and then with that, you can sync your view to incorporate Google Earth as the background. So here I can kind of scroll around, and if we have a corridor that we're aware of that may already exist, and this is a nice way that you can actually create the path relatively quickly. So the way in which you do this is if we look at the blue line, this is following the path of my pipeline. Obviously, there is going to be a little bit of correction or understanding of where the pipeline is in the right-of-way. On the transmission line side, if you have satellite imagery, you can typically see the location of that. And the way that you would draft this is simply going into your line tool and drawing a line. And I typically will draw this line from one tower to the next. And the reason I do that is so that you get a good segmentation or a location when you import the MicroStation or DXF model into XGS Lab, because XGS Lab can read each of these lines and determine the starting and end point of that. So once we've created our outline of the corridor, what we can do is save this as a DXF, then switch over to XGS Lab here. So here I have my XGSA FD model, and I just need to set my reference standard, and my frequency will be 60 Hertz. For this, I'm just going to use 100 ohm meter soil just for stepping through this. Main thing we want to do here is import that model that we've just drafted in MicroStation. So we'll point to the DXF path, and then I can just import the layers that were drafted. So here, the 0 line or the 0 layer, that was associated with my transmission line. So we'll give that the overhead line characteristics, and I will give this a tag name of phase A and apply this. I'm also going to pull in the pipeline. This will be electrode 2. And the characteristics, you obviously need to edit that in your XGSA FD library. So we'll choose pipe type and pipeline here. And I do need to shift this down into the earth 4 feet. And one thing I need to highlight as well. So in MicroStation, you can place the appurtenances by using a cell. So right here, there's this little crosshair that's one of the cell. This is often referred to as a block in AutoCAD. Both of those can be read by XGS Lab and imported to note the exact location of different test stations, valves. So we can do that by adding another element, going to the pipeline, call it the conductor. I've already added a conductor type, that's the pipe appurtenance. I'll just call this a test station. Again, I need to shift this 4 feet into the earth. And then here's where I can pull that block or cell name and then assign the length of that. So this is going to be a vertical element that's being imported. So I just hit import on this. And a couple seconds later, then we'll have a list of our conductors. So here we have phase A, pipeline, and test stations. When we go to our draw view, we're going to see pretty much what we saw in MicroStation. And first stage I need to do is I need to create 3 phases of this system. So I will filter my view for phase A by doing my tag filters, select the phases, and then I'll just do an offset of -23 feet, since that's about the separation that was seen in Google Earth. And now what we'll have is a second set of phase conductors. So if I zoom in, you can now see I have phase A. This is another phase, but it has the same tag name. And that makes it a little more challenging for me to do some edits in bulk. So what I do is I go back to my list view, and because I created this conductors after this importation, it's easy for me to select and determine this is actually the new phases that I'm going to describe as phase B. I need to switch this over to be a source as well. And if this is a 230 kV line, that would be 230 divided by square root of 3, which is 132 kV. And I'll put this as -120. And we can load this with 1,000 amps in our phase conductor. So now we have phase B. When it's loaded, I also need to do the same type of source energization to phase A. So we can do that going to my conductor editor and through the list view as well. I'll switch this to be a source. Polar. again with 1,000 amps as the load current, 0-degree angle. So now I have phase A, phase B. Now, if I want to create phase C, once I offset this phase B, in my list view, phase B, the original here, will be followed up by the phase B that I just offset. So what I do to create a little separation is I will create a new tag name. So we'll just call this flag, for instance. And it doesn't really matter what I call this or what I use, but it gives me a little line that in my list view, once I've created a new offset for my phase B, I have a little indicator for where my new conductors are located. So again, we're using that offset tool in XGSA FD. Obviously, if you needed, you could do all of these types of CAD-related drafting in your CAD tool of choice. But I do want to make sure to illustrate how we can optimize our use of XGSA FD. So here we have this little flag conductor and then phase B down below. So I know all of these conductors are what I've just offset. So I can call this phase C. Going to polar format, I will just remove the negative from each of these. So now I have 3 phases in my power system, and we are pretty much ready to run my analysis. I do have a couple things I want to do. One of them is that this pipeline, it is parallel-ish to our transmission line for a little over 1 mile, so 6,000 feet. So I have some concerns that this length of this pipeline is not sufficient to fully model my system, meaning that if I run this model right now, I could have end effects because this pipeline is a coated material and can hold that voltage for a much farther length than what I have modeled here. So what I can do is either extend the length of this pipeline or use the simulate infinite lengths. And what this does is it eliminates this artificial high impedance, so you don't get an artificial voltage peak there by inserting a transverse impedance. So that's one little efficient method to providing the little ends to your pipeline model. Pull one from both sides here. And with that, we should be ready to run our analysis. So I'll go ahead and hit debug and compute. Okay, so one thing I've ignored is I forgot to elevate my phase conductors as described by the air conductor. They are on the soil surface. I need to actually elevate phase A, B, and C. So we'll go ahead and do that. This also reminds me that I should really put some sort of sag characteristic on those as well. So first, let me elevate these phase conductors so they are 85 feet into the air. So this is going to represent their attachment point. So when we go back to our draw view, we'll be able to see when I zoom in, these phase conductors are now represented 85 feet into the air. But I also want to consider that sag or that characteristic that we saw in our planar profile. And I can do that or calculate that by using this catenary curve tool in XGS Lab. So we'll first specify the length and the sag by using this W and Z coordinates. So we'll say we have a starting coordinate of 0 with a height of 85. Then we go halfway to, let's say the total span length is 1,200 feet. So this 600 is halfway. We'll say it sags 40 feet. Then we'll put an endpoint of 1,200 and the height of the attachment, 85 feet. So then we get this catenary constant. This is what we can take, copy that, go back to my drawing view, or actually I'll just go to my list view. And if I filter my tags to A, B, and C again, I can select all these conductors and in my layout, put in that catenary curve. So when we look at my draw view again, what we'll see when we zoom in is this curve is approximated in XGS Lab. So it's kind of a handy little way of modeling this with pretty good accuracy. So now when we run, we should have no errors and be able to get the steady state analysis results. And this will just take a few seconds while that runs. What I usually find is that in these studies, who you're dealing with on either the transmission or the pipeline side, the goal is really to set expectations and make sure it's clear on what information you need to do your study, because there's different industries, different expectations, and different backgrounds for a lot of the engineers involved in these. So trying to make it clear what information is useful is beneficial to everyone as these projects progress. So we've finished our analysis. We have a new analysis tab here. And one of the things we can do is look at the voltage on our pipeline. So I can do this by going to view 2D. So we kind of get a top-down view of this, and we can see there's only 6 volts that are induced on this pipeline. And we kind of get a peak right as we change the geometry of the relationship between this pipeline and this transmission line. The other characteristic, so looking at this, we are well below that 15-volt limit that's typically applied more towards the appurtenances or where you might have test stations. Regardless, we can still plot a 1D plot. And one thing you can do is set the 1D plot consecutive, so it's going to automatically connect those, as well as put in my 15-volt limit. And I need to increase my maximum for my display. So here we get a nice 1D view of the stationing as well as the voltage limit and what our voltage profile looks like on the pipeline. We can switch over to the leakage current through small holiday. So this is that AC corrosion concern that we're concerned about. And usually the criteria is using a 1 centimeter squared holiday hole. So that's 0.39 inch diameter hole in that coating. And we'll keep the pipeline filter, and this time we'll use 30 amps per meter squared. That can be the limit. We'll do a 1D view. And again, we can see we are below that 30 amp per meter limit, and I will adjust my maximum value so we can display that as part of the final results. Now this is just a steady state and would indicate that everything's fine. We don't need to do anything as far as mitigation goes for steady state analysis. We do need to do some things for our fault analysis. So doing a fault, just even a fault through the corridor, it's as simple as selecting phase C. And we can change my conductor editor. Instead of 1,000 amps, we'll say this has 20,000 amps that go through this corridor in the event of a fault at a point further down. And we don't need phase A and B as part of this model because the magnetic field is dominated by that phase C. So we can simply disable this, save a little bit of time on our analysis. And I've been playing around with this model a little bit. My primary concern is going to be this test station, which I need to modify so it's above the Earth's surface. So right now, that test station went below Earth. Now I've got it elevated. So both test stations will have an issue for them, but I want to apply mitigation to one of them. And a common mitigation method for resolving touch voltages is called a gradient control map. So this is simply just a mesh of conductor that will go around our test station or whatever appurtenance you may be dealing with in order to reduce the voltage gradients between the pipe, that test station, and the surface of the soil. So we can do this going up to our draw view. I'll call this my mat. It doesn't really matter what conductors I'm selecting right now, we're just going to make a little mesh. So I'll use 1/0, and we can use this, put this at a buried depth of 1.5 feet. And usually I'd be pretty specific as far as how far the mat extends from the test station, but here I just want to make a quick illustration of one methodology to mitigate these systems. So this is about 17 feet long, so we'll make a short array of these. Do a couple more. I'm just doing a 2-foot spacing. Typically, actual gradient control mats are going to have a much tighter spacing. So this is just going to be a nice little approximation using XGSA FD. So apply that. Extend the one conductor too far. And I do want to make sure I have a conductor that's connecting from my let's see. What I can do is I do want to make sure I have a conductor connecting to my gradient control mat from that pipe or from that appurtenance. So I just ran a conductor from there. So now we should be set to do our fault analysis, or what I'll call my through fault analysis. I do need to understand the clearing time associated with that, so we'll make this 0.2 seconds, and we could run the model, assuming there's not been any sort of overlapped conductors. I did. So we have one conductor that's overlapping right there, so I'll just delete that. And so this is going to give us the a view of the through fault scenario. So we're having much more significant induced voltages on the pipeline. So we'll look at the potential of that pipeline. And if we just look at the pipe down on a 2D view, let me expand my view. We'll replot that 2D perspective. There we go. Now that we have this fully encompassed, so we can see we're almost at 2,000 volts in these red areas that's induced on this pipeline, which means at our appurtenances, those are probably about 1,000 volts and 2,000 volts. What we'll see if we zoom in on my non-mitigated appurtenance, if I do a little area calculation around that, I can plot the element, and I can do a quick search for just touch voltages to that test station. I can control my search to be 6 feet or 4 feet from that test station. And what I can see is my maximum touch voltage is about 1,000 volts. And if you want to see the non-filtered view, we can see that here because the pipeline voltage is so much higher than the Earth's surface potential. But if we go to our other test station where we have this gradient control mat, if you recall, this actually has a higher voltage than the one we were just looking at. I'll go back to my area calculation and redraw. So we've recalculated the Earth's surface potentials up at this appurtenance. Again, I will set my reference to just look at the test station of the touch voltages to that, plotting my safe areas. What we see is this green indicating that we are actually below the compliance criteria for my EEE 80. And what we've done is essentially we are making the Earth's surface potential elevated to match the voltage of that test station. So there's a reduced touch voltage overall. So that's one common methodology for analyzing and mitigating for steady state and faulted state. Of course, I do want to highlight what happens if we do have a steady state concern. So we'll go to our tutorials. So one of the tutorials in XGSA FD has a nice long parallel corridor. And if we look at this system, I think it's about a mile or two of parallel section. And again, we have the infinite length of this pipeline on either side. And what I want to look at is the overall induced voltages on this pipeline. So we can go to the potential. I'm just going to filter my view to look at the pipe, do a 2D view. So we can see, once again, we have some elevated voltages right around this point, kind of as the corridor geometry changes of about 20 volts. If there's an appurtenance there, that can be a touch voltage concern. We'll look at the leakage current as well, and we'll use that 0.394. And what we see is we are well above that 30 amps per meter squared for a lot of this corridor, especially if you switch over to the 2D view. And again, this is going to align almost identically to the pipeline. So what do we do to mitigate this type of concern? There's a few things. One of them is that we can take an analysis approach to either ground these voltages, so we can actually add direct grounding to them. And I have a prepared model. Let me pull this up. So here I have a model. If I go to my draw view, we'll be able to see a lot of conductor has been added to this. So I'll filter my view. So I describe this with the tag filter of MIT. But all of these locations are locations where I'm bonding to the pipeline through some solid state decoupler or other device, so that we can reduce the overall voltages on that pipeline. What we can do is look at the results going through the distribution, looking at the potential here, and again, doing the same type of filtering to look at the pipelines induced voltages here, as well as now we can look at the leakage current on the small holiday. And this was the primary concern. We wanted to see that below 30 amps per meter squared, which we're right at that value almost right here. One thing when you're doing these studies is that I typically would recommend going a little heavy-handed with your mitigation and then taking a step back. So what I would typically do as an analysis process is we have these 4 areas where we have mitigation added. Well, if I wanted, I can make 4 mitigation cases where I look at what happens if I just have one of these in there and see if that makes a difference. So we can take a quick look at that. So I'll open up mitigation 4, for instance. And all I do is I actually just put in what I think would be an excessive amount of mitigation, and it's easier to step back from that. So I want to show in my draw view, if I filter my view to just that mitigation, now we just have this one section of ground conductor. And we can plot it again through our distribution view, see the leakage current through the small holiday, and just look at the pipeline. And right there, you can see pretty clearly we didn't mitigate this side at all. One efficient way to do it, though, is by using the scheduler. So I'll close this. And because I created multiple scenarios kind of stepping through the full mitigation versus some half steps to that mitigation, I can use Scheduler to create a list of all the files that I want to run after I've kind of made my multiple scenarios, and just hitting the little check mark that allows me to hit the compute and run that analysis. When you do that type of analysis, what you get in the project folder is a CSV report automatically generated. And from that CSV report, you can just simply, in your project folder, filter for the CSVs, copy those over, and put them into a nice little spot with making it easy to use Excel to pull in that information, because in Excel, you can just point the file towards a folder and pull in that data. And this is something that if you put in more files, you can automatically create it, and it creates this nice table for you. And then here, I can do a nice little comparison to see, okay, how much benefit do I get from mitigation 4 going to mitigation 3 or 2 versus mitigation 1, which was my entire model having grounding, extra grounding to it. So I might step to something more like mitigation 2 or 3 because you get similar results with less ground conductor used. And you can use that same type of scheduling tool in analyzing faults as well. So if we open up this model, and I'll break here for questions in another couple minutes. So again, I do invite people to throw out questions as they think of them, either about the software or related to this analysis process. But I want to highlight, if you're using fault studies, we looked at a through fault, meaning currents going just through the corridor, only inductively coupled. If you have faults along the towers, you can use the references in XGS Lab to put in these flags. And I give each one of these a specific name, like P1, P2. So when I use the scheduler tool again, all I need to do is pull in that kind of base model for my faults. And then if I right click on this, I can do parameter editors, do a little addition to do energization. And I'd simply call it P1, P2, and so on, P3, describing I want 20,000 amps. And then the model will automatically insert faults at each one of these points. So what I end up with is, exit this model, I have a fault at position 1 because how I energized it using the scheduler tool. So these are a couple things that you can do very large studies automatically using a combination of the scheduler tool, CAD programs to insert information and export information, and typical Excel sheets. So we'll look at the fault here, and you can see in this tutorial fault underscore P1, which is automatically created by XGS Lab, we have a fault at this point. And therefore, we can take a look at the touch voltages right here, calculating the air surface potential, as well. We'll also take a look at the coating stress along that as well. So we can look at the touch voltages related to the pipeline, which are pretty significant, about 3,000 volts looking at the legend. And you can see if you look at the unmasked version, we actually get increased voltage, touch voltages as you go away from this tower, because this tower is actually putting in ground potential rise, which is elevating the soil voltage, which is closer to the pipeline voltage. So at the tower where you're getting this transferred voltage, you actually have a lower touch voltage, and away from the tower, you have a higher touch voltage. This is also something we'll want to look at the coding stress for that. So we can go to our covering stress voltage and just look at that for the pipeline. So we can see we're exceeding this 3,000 volt criteria, which depends on the type of coding that's being used, whether or not that is going to be an issue or not. So that's just a few of the features that are kind of one methodology for using XGSA FD in combination with other tools to efficiently analyze these systems. There's several different methodologies, so it kind of works whatever system works, whatever way you've received information so that you can do your study. So at this point, I'm going to switch over to do some questions. Hope I do a few minutes of this. So first question, does the medium in the pipe, meaning if the pipeline is carrying water, oil, sewage, have any bearing on the propagation of fault along the pipeline? What I would say is it typically does not, as long as you have a continuous metallic pipeline. Where it does play a role is if you have some sort of insulating joint. Typically, there's a what we'll call a flange kit or some sort of isolation that's meant more for DC. That can be a concern when you're looking at AC voltages, especially induced ones. Often you'll end up puncturing that flange with the amount of voltage you induce or conduct to a pipeline. So there's other types of insulating joints that have a higher threshold, as well as you might go to some sort of solid state decoupler to shunt around that. If you do have an insulated joint that is able to withstand the voltage that you're inducing on there, you can have conducted voltage through your medium like your water. So you may need to increase that length because you may think that you're actually isolating one portion of the pipe from another, but really it's going through that medium. Another question is, can we use XGS to calculate induced voltages on ungrounded shield cables? Yeah, so if the cable's ungrounded, then you won't have that induction as much, but once it has a connection point, then you can have some current going through it. If you do have ground on both points of that shield, then you can have the induced voltage and current on that cable, and that's something that you can analyze with XGS Lab. One thing I do want to highlight too, what that question brings on, is there's these screened conductors, which is one methodology for modeling both gas insulated switchgear or busing, as well as cables. So you can add in insulation on the exterior of this to pretty much create a cable in the model. So the software itself is pretty flexible. So whatever you have in the real world, you can model in the software and approximate what the electromagnetic effects are going to be for that. I think that is kind of the majority. Again, I do want to say that this webinar will be recorded, so we'll be able to view this later on. And do appreciate everybody jumping on this webinar. If you can, do let us know your thoughts on the survey afterwards. I definitely appreciate any critiques or requests. And if you do need to contact me, feel free. My name is David Lewis, engineer here at EasyPower. So my email is david.lewis@easypower.com. So we've gone over the hour just a minute, so I will conclude this webinar, and thank you everybody for attending. Very much appreciated, and I hope this was a beneficial webinar for everyone. Thank you.